パイナップル1という台で、FPGA と 4GPI を備えた論理ゲートとメモリ AC だけで構成した自家製30ビットRISC-Vとなります。チェコのフリップスカンデラさんからです。Hello, this is Niwa. I'm a moderator of the afternoon session. So the first session of afternoon by you, the title is Pineapple One, that is homemade 32-bit RISC-V CPU made only out of basic logic components and memories, no FPGA, no microcontrollers. And then I introduce you. So presenter's name is Filip Szkandera. Is it okay? Sorry, that's so. And he is a higher school and secondary school. He's a student of higher school and secondary school of electrotechnical engineering in Olomouc, Czech Republic. So, will you start your presentation right now?
Yes, I want to share my screen. And here is my presentation. So, can I start now? Is everything all right?
Please.
Good. Okay. So, hello and thank you for inviting me to this conference. It is a great honor to be here. My name is Filip Szkandera, and today I will present to you my homemade 32-bit RISC-V CPU that I've been building for the past 2 years. You can contact me on my Twitter at 10philip or drop me an email if you have any questions. But before we start, I would like to introduce myself a little bit more. I come from a city of Olomouc in the Czech Republic. I'm 19 years old and currently I study at higher school and secondary school of Electrotechnical engineering in Olomouc. Well, I hope to pass my final exams in about a month, and then I would like to go to university. I am interested in CPU design, and I'm a huge RISC-V fan. But even before we get to my RISC-V CPU, I would love to show you my first homemade CPU that I've made about 3 years ago. It is also made only out of discrete components, and it is based on CISC architecture. I was pretty happy with it, but I felt kind of limited by the architecture itself. Luckily, about a month after I have finished it, I've discovered RISC-V. So I've read everything that I could find about RISC-V, and after studying the official documents and even reading part of a book, it just all clicked for me. I found it more standardized and it really made much more sense for me. But one of the biggest advantages, of course, is its open source license, which is not seen in many other architectures. And here is a little sneak peek of my device. On the left image, you can see it without the case, and on the right image, you can see it with the case cover on. I will make a live demo here at the end of my presentation, so you could get an idea how it looks and how it feels maybe. But before that, let's talk about some specifications. My CPU is based on a RV32i standard, which is the bare minimum for any RISC-V CPU. It is made only out of discrete logic ICs, like, for example, 74HCT245, and memories, mainly EEPROMs. Clock frequency of my device is 500 kHz, which is okay for me. It also has a RAM, I/O port, and an instruction memory inside. So basically, it is a very, very simple computer. Here you can see a 3D model of the whole CPU. The main core, which is located inside the case, is made out of 9 PCBs that are stacked in a tower-like structure, connected together only via pin headers. That means there are no dangling wires between the individual layers. It also integrates a very simple FPGA card with a resolution of 200 by 150 pixels. It has 4 I/O ports and a USB-C connector for 5-volt power. The entire case was printed using Prusa 3D printer. Every layer has its main purpose, as you can see here, but as I will show in a minute, some layers can serve multiple purposes. I've made every PCB fit into a 10 by 10 centimeters area to lower the production costs. This has a pretty significant benefit. Everything is modular, so I can fairly easily swap any PCB for a potential upgrade or repairs. Well, on the other side, this made debugging much harder, but you will see in a minute how I've tackled this problem. And here is a block diagram of my CPU. Each arrow represents a 32-bit bus line. I took a lot of inspiration from a book by David Peterson and John Hennessy called Computer Organization and Design RISC-V Edition. In some cases, I've managed to fit more than one block onto one PCB. For example, the immediate generator shares the same PCB as the instruction memory. These modules can be found on the left side of my block diagram. Well, to give you some idea about the whole project, I have divided it into several phases. First, I did simulation, and it took me about 5 months. At this point, I have to explain that by 5 months, I mean 5 months, and the whole project was done in my free time. Then I've designed PCBs. It was a pretty lengthy process, which took me around 8 months to finish. Later on, I have created a prototype version first to debug the design flaws, and this took me almost 5 months. After everything was tested and was working correctly, I've assembled the final version. So here is the simulation. I've simulated my CPU in a program called Logisim Evolution. I've tested its main features and the overall design. Well, I know this isn't the best program for simulating a complex CPU, but it is free and it helped me quite a lot. And here is one of the 9 PCBs, which I've designed in the Autodesk Eagle. I then sent it to a Chinese company called JLC PCB for manufacturing. After receiving the boards, it was time to solder every IC by hand. Well, as you can probably imagine, it was quite a tedious job. And this is the prototype of Pineapple 1 that I call Pineapple 0. Well, nothing ever works on the first try. Or does it? No, it never does. So I've decided to make a prototype version first. I've tried to separate everything into its own sections to make it as modular as possible. And I've also added a whole bunch of test points all around my PCBs to make the debugging process at least a little bit easier. And of course, debugging, especially in such a large project. You might think that some high-tech lab is needed, but this is not the case. At that time, I didn't even have a proper oscilloscope. So my only option was to get creative. I've designed 32-bit readers that could be attached to bus lanes. You can see it here on the right image. These readers would collect as much information about the current state of CPU as possible. I wrote a Python script to collect these data in real time and compare them to a prediction. And if there was some inconsistency, my Python program will command the CPU to halt immediately and will alert me. And I will take a look and take over. And hopefully try to find that error. It was pretty tedious. I've spent at least 3 months purely just debugging this prototype. After everything was finally done, it was time to assemble the final product. And here you can see all the parts I used to build my CPU. Programming my CPU is very easy. First, you'll write your program in a C, and then you compile it to the binary file using the official RISC-V compiler. Then my Python program pushes this binary data to my CPU programmer using a USB cable. CPU programmer converts this data to a serial stream and loads it to the CPU using a standard RS-232 cable. Once this connection is established, well, at least for the first time, you can simply start uploading new files anytime you want, without any reconnecting or resetting. Everything is happening automatically. Well, and now I guess it's about the time to show you the real product in action. So here you can see the device in its glory. The main case is divided into two parts, the bottom part and the top part, or the lid. These two parts are held together by 3 screws. Here, and one on the other side as well. Here. I've removed these screws before the start of this demonstration. Oops. So you can see the device in its glory. The main body or the case is divided into 2 parts, the bottom and the top part. These parts are held together by these 3 screws that I've removed before the start of this presentation to save a little bit of time. After this is all done, I can just slide and open the lid like this. And here you can see the CPU core itself. Like I've said, it's made up of 9 PCBs stacked in a tower-like structure, and there are no dangling wires between these layers. Everything is connected only via pin headers. The only wires you can see here are for connecting the CPU core to the front panel. And speaking of the front panel, here is the USB-C connector for 5-volt power, the on and off switch, the LED indicator, the reset button, the programming port for connecting the programmer, VGA outputs, and 2 inputs and 2 output ports. These are called port A, port B, port C, and port D. I need to mention that in this CPU core, I've used more than 230 individual integrated circuits, which is quite a lot. So now it is time to connect and show it in action. I have here a 5-volt power, which I can attach here, and turn on the CPU. Now the CPU is running and executing some instructions. Well, and to better demonstrate its functions, I've created, firstly, this little touch module or button module, you can say, and we can connect it to a port B. To see some action or to see something happening, I've created, I will show this little LED module with 8 LEDs on it. I've pre-programmed this CPU with a little animation, and I can choose between my animation or between my predefined animations based on my little keyboard. This is really basic stuff, but if we want to do something more with our CPU, we can go and use my PS2 adapter. So I can attach it to a port A. I don't know if you can see it. Oh, and grab a PS2 keyboard and connect it to my CPU. At this point, I can start typing some commands, but we do not see any output. So for that, I will connect an external VGA monitor. I'm using a VGA to HDMI adapter here, but I've tested it on a purely VGA screen as well, and it worked just as fine. So here you can see my program that I've pre-programmed as well, and I call it PineShell. It is a very simple shell-like program, and I can type some commands like hello, or to display system information, I can type system information, and it will show system information. I've programmed a peek and poke command as well, so I will show you a poke command. I will type poke and address and my data to be written to that address. I've chosen this address because it is mapped to this video RAM. So on the beginning or on the left side, you will see a 54 appearing in binary. And you can see it. There are some pixels that appear right there. We can clear the screen using a clear command, like so. And if you are bored, I've even made a really, really simple snake program, which I can control from my keyboard with my arrow keys. The goal is to collect these question marks and get longer. This is just a demonstration of what this CPU is capable from. This, of course, it's a RISC-V CPU. It can run a lot more more complex programs as well. But currently, I'm having some engineering issues with the PCB design that prevents me from writing more complex programs. But this is just the beginning, and I'm sure I will improve it later, maybe we can say. Well, this was everything from my presentation. Thank you very much. And thank you very much for
Thank you for a good presentation, and yeah, you're quite effective experimental job, I think. And so that's so question from audience. So I have several one. Firstly, this RISC-V computer, which specification of RISC-V is the base of your computer? Is this a kind of yeah, RV32 something, or?
Yes, I'm using the RV32i design like integer. This is the bare minimum, but yeah, I wasn't able to fit anything else to this structure for now.
Oh, so then I think this RTL and the PCB circuit is created by you from scratch. Is that right?
Yes,
Oh,
yes. I've designed every block,
so great.
every module from scratch.
Okay, so great, very great. So, and so I have, yes, related simulation. So, yeah, you showed us some simulation step. Maybe you use some simulation tool or some C library or so. Which do you use? Sorry, maybe you already talked about this, but I want to know about actually which simulation tool you use.
Yeah, I've used the Logisim Evolution, which is just a playground for some ICs. We can say we can connect logic gates together, and this is not really made for designing a CPU, but it really helped me. It was free and quite intuitive, so I constructed and more complex blocks that I've chained together, and with more and more blocks, I've created this CPU.
So you can use some open source library such a discrete component. Is that right? So sorry, I have not so much to experience such a from scratch with discrete device anyway. So it's very fantastic one. So
By discrete, yes, this is by discrete. I mean that I didn't use any FPGA or any microcontrollers. These are these tiny little chips that serve only one purpose, like for example buffer or AND gate, and like so.
Yeah.
So I don't have any complex ICs, and this is by design. I wanted to. Well, it was quite a challenge, let's say, like it.
So yes, discrete means that just a NAND or gate, some logic gate only. So then you make some logic gate design and you simulation such a such level. There is a tool to simulate. Then you can go it again. So great. And the next debug situation. So maybe you have some problem during the debug, and maybe you needed to modify some fix or solve the problem on it. Which problem? What is the most serious problem you find in your design?
Well, in this particular situation, I've used a lot of Python, which I used to verify some designs. I've used to compute every ALU output to compare it to my existing ALU in the design. So it is well, to correct that everything is working, I've also used Python to connect to my prototype and to gather all these data from these readers that would later then compare it to my, and again, Python prediction. And this really helped me in the developing process.
So this is good things from at such a discrete device system. So every signal lines can be found, can be checked by the probe or something. So if you have some problem,
Yes.
then you can check each line of component there. Yeah. So debug is okay, but
yes.
Then and okay.
Yes.
Yeah. So such a
we can say that the exposement of the individual signals is a benefit, but if we have this many signals, and this being a 32-bit system, this can be quite an understatement that it was easy. There were a lot of problems that I had to solve beforehand, before even running this simple bind shell program.
There are comment and question from audience. Yeah. So first comment, it's incredible that so only logic gate discrete it's combined to the CPU and within the function module, and is a very small PCB box. It's very incredible. It's great things. One comment, yeah. And next one is a comment and and next one is a comment and question. So first comment, great work. And question is, what kind of equipment could you use for debugging? So debugging. And his imagination. So yeah, he said.
Yes, I've talked about.
Please say.
I've talked about it a little bit. I've proposed an oscilloscope for a while, but mostly I've used my own readers to collect my information, and some cheap USB logic analyzer, which is only 8-bit.
Oh.
But the most of my work was happening in my simulation, and then I've compared this simulation to my current state of CPU, and that really helped me quite a lot to find my problem.
Okay, so then you can compare the value between the simulation and the actual test on your board, yeah, and checking the program. So
yes, I've set up these simulation to that point that I really saw only what I needed to see, and this more just helped me in this way. The simulation is really made to debug this CPU.
Okay, so then the question of audience also, yeah, he guess you use a logical analyzer. So yeah, you said a small logical analyzer you use, and yeah,
yes,
it
really
must be
small,
really tough.
8-bit.
8-bit. So okay, it's just a moment, please. Next. Okay, so it's just a moment. So okay. Thank you for presenting. It's the time to the next session. It's just ongoing. Yeah, your job is very great.
Thank you very much.
Very, yes, incredible. Yeah, so it's very effective, and so encourage other person to make anything or describe. So thank you so much.
Hopefully.
Thank you for presentation. Yeah. So we will.
Thank you. Goodbye.
Come to the next session. Yeah. So thank you. Bye.